Okay, so thanks to Darshan Bhai for arranging all this anyway. So today is lecture number 20. Lecture number 21. Uh, by the way, there are some queries about projects. Can we do 7 students can do the project or not, right? So remember, if you increase the team size, the amount of work has to be proportional, right? So don't just like that keep on increasing, and then if there is a small amount of work, whole thing will be a problematic thing, right? So just make sure that if you are making team size more than 6 or 5, you need to have the significant amount of work in that case, right? So people who are requesting me to increase the team size. Okay. Okay, now, so we were looking at harmonic functions. Let me go to the slide where we were looking at this stuff. Again, I am asking you to read something, because either you read notes or something. Daily, I get for the entire 4 or 5 courses, whatever you are doing, you need to spend at least 5 hours daily, Monday to Friday. Okay. Otherwise, there will be issue. If you are not reading anything, then there will be issue, right? Because reading is the habit that most of you are not having it now. Okay. So I gave you this idea of harmonic function. So harmonic functions are 2 variable functions, okay, which satisfy this equation. This equation is known as Laplace equation, that del square h is equal to 0. H is a harmonic function, it's a 2 variable function if del square h is equal to 0. Right. In other words, if del square h of del x square plus del square h of del y square is equal to 0, right? You differentiate h 2 times with respect to x, then add 2 times differentiation with respect to y, and this, if it turns out to be 0, so this equation is known as Laplace equation. I mean, this is very popular one. So then this function is known as harmonic function, right? And as I mentioned to you, that in a beautiful scenario, if f of z is an analytic function, then the component functions u and v automatically turns out to be a harmonic function. If f of z is analytic function, right, in D, then its component functions u and v are harmonic. Okay. Anyway, because if f of z is analytic and you can do, I mean, the Cauchy-Riemann equations are satisfied, we also require another condition that it's for example, why we are able to do these things, because the partial derivatives are continuous. That condition is there, otherwise you will not be able to do this, right? And so u and v are harmonic. Okay, that we have looked at it. Now I want to give you some idea of what is known as harmonic conjugate. What is the meaning of harmonic conjugate? So suppose f of z is equal to u plus iv is an analytic function. So it's analytic in D. What do you mean by analytic? So a function f of z is analytic at a point z is equal to z naught if it is not only differentiable at z naught but also in the neighborhood, right? And if the function is analytic at every point in a domain, I mean, so then we call it analytic in the domain, right? For every point if it is analytic. then u and v are harmonic. This we know, right? Means del square u is equal to 0 and del square v is equal to 0, right? That condition is there. Now suppose, it's a very interesting scenario. Suppose you start with a two variable function uxy. So a real function I am talking about, which is harmonic. I am not worrying about any f of z or anything. Some two variable function. Pick up a two variable function u of x comma y. So two variable function which is harmonic. Sorry, which is harmonic. Means del square u is equal to 0. This implies that we have del square u is equal to 0. Now, if you can find another function v of x comma y, some another two variable function which is also harmonic. Means del square v is equal to 0 also. So you started with a two variable function u which is harmonic, right? And suppose you are able to find another function v, two variable function which is also harmonic. Okay, so that they satisfy Cauchy-Riemann equations. See, this is a way of building analytic functions. So I am saying that you start with a harmonic function u, some harmonic function, and suppose you are able to find another harmonic function v, two variable function, such that u and v satisfy Cauchy-Riemann equations. Okay, then we say that v is harmonic conjugate of u. Okay, if they satisfy Cauchy-Riemann equation, that's a very stronger condition. Okay, then we say that v is harmonic conjugate of u, and in this case f of z is equal to u plus iv will be an analytic function. In D. Okay, so this is another way, a mechanism for building analytic functions, right? You start with a two variable function which is harmonic, try to find another harmonic function v such that they satisfy Cauchy-Riemann equation. Okay, so then you can take u plus iv and that will give you analytic function. Okay, so let us do one or two examples. So in fact, before doing this, I just want to mention a theorem. A function f of z is equal to u plus iv is analytic in D, in a domain D, if and only if v is a harmonic conjugate of u, right? This is the results, right? So as I told you, if u is a given harmonic function and if you are able to find another harmonic function v such that they satisfy Cauchy-Riemann equation, then function is analytic, right? Now example, suppose u is given to you x square minus y square. ध्यान से देखना है इसको, and vxy we are able to find as 2 times xy suppose. So of course you can check that u is harmonic, del square u is equal to 0 and v is harmonic. So del square u is equal to 0 and del square v is equal to 0, right? You can check that, na? And also del u over del x is equal to del v over del y and del u over del y is equal to minus del v over del x. Can you verify this for this 2 u and v, right? This implies that the function f of z is equal to x square minus y square plus I times 2xy is analytic. And you can clearly see that what is this function actually? Z square, right? If z is equal to x plus iy. Okay, starting with 2 variable function u, we are able to find another function v, harmonic function v, such that u and v satisfy Cauchy-Riemann equation. So we are done. Now I am going to, so that means here v is the harmonic conjugate of u. So note, v is the harmonic conjugate of u, but u is not the harmonic conjugate of v. Do you mean by, it's very important thing, you see. If I interchange the role, okay, what about this function 2xy plus I times x square minus y square? Now I have interchange. Is this a whether, so basically here v is a harmonic conjugate of u. So I am saying whether u is a harmonic conjugate of v or not here. What is the condition which is violating? Any idea what is happening here? This function, of course, both u and v are harmonic, that is not an issue, right? But if u is this, so in this example u was x square minus y square and v was 2xy. But if u is this and v is this, what happens to the Cauchy-Riemann equation? Del u over del x is how much? 2y, okay, and the other one is del v over del y will be what? Minus 2y. They are different. So Cauchy-Riemann equations are not satisfied. So actually, although v is harmonic conjugate of u, but u is not harmonic conjugate of v. See the beauty, and hence this function is not analytic. So you know that this function is not analytic, right? समझ में आ रहा है ना? ये बहुत छोटी सी चीज है, राइट? कंफ्यूज करने वाली भी है कि ऐसा क्या हो रहा है, राइट? If u is x square minus y square and v is 2xy, both u and v are harmonic, no problem, and they satisfy Cauchy-Riemann equation. So the corresponding function x square minus y square plus I times 2xy is analytic, no issue. But if we interchange the role, if u is this and v is this, then Cauchy-Riemann equations are not, although the component functions are harmonic, no problem, but the Cauchy-Riemann equations are not satisfied, and hence this function is not analytic, right? Right, because I think del u over del x is equal to how much? 2x, right? 2y, and del v over del y is equal to minus 2y. So Cauchy-Riemann equations not satisfied. So this is not analytic, right? So this is something, you know. So that means we are saying that although v is harmonic conjugate of u, but u is not harmonic conjugate of v in this example. Okay, it's clear? छोटी सी चीज है सोचने के लिए, राइट? Okay, another example. Suppose uxy is y cube minus 3 x square y. and we ask you find the harmonic conjugate of u. How will you find harmonic conjugate? U is given, two variable function. First of all, ये क्या हो गया? ये कट रहा है something, right? Can you see this or no? Daily there is some problem, right? Find harmonic conjugate of u. Okay, that's a question. So whether u is harmonic function, so you can just check whether del square u is 0, which is obvious, right? That's not a, so u is harmonic. So the thing is that note that del square u is equal to 0. So u is harmonic first of all. Okay, fine. Now we want to find a harmonic conjugate of u, means I have to find a function v which is harmonic and u and v satisfy together Cauchy-Riemann equation, right? So that means we have del u over del x is equal to, so I have to find v, vxy is question mark, such that del u over del x is equal to del v over del y and del u over del y is equal to minus del v over del x, right? So v is unknown here, u is given to us, substitute कर देते हैं और क्या है, so simple calculation. So this equation will give, this is 1, this is 2, 1 will give you that vy is equal to minus 6xy, right? Correct? u को डिफरेंशिएट करिए विद रिस्पेक्ट टू x, y क्यूब टर्म चला गया, minus 6xy, right? Partial differentiation, right? Now, so vy is given to us and now integrate this with respect to y, keeping x constant. So if we integrate this, we will get vxy is equal to minus 3xy square plus, we are integrating with respect to y, keeping x constant. So जो integration में constant term use होता है, that could be a function of x also, right? I mean that will be a function of x, some phi of x which we don't know, okay, some arbitrary function of x. So we have integrated with respect to y, keeping x constant. Okay, this is how this function will be, right? So vxy is this. Now using equation 2, what will happen? Using 2, we will get 3y square minus 3x square is equal to 3y square minus phi dash of x. This is differentiation with respect to x. Simplification, this simplification will give you phi x is x cube plus c, some constant c. I mean, so here phi dash of x is equal to 3x square actually, and this will give you phi x is equal to x cube plus c, right? 3y square cancel हो गया, right? So phi dash of x is 3x square, so phi x is x cube plus c. Now this time it's because integration with respect to x, there is only one variable involved, your constant is c only, right? There it was phi of x because the partial differentiation was involved. So that means v of xy is what? V of xy is minus 3 times xy square plus x cube plus c. And so this is the required harmonic conjugate. In fact, the function, analytic function f of z will be y cube minus 3x square y plus I times minus 3xy square plus x cube plus c, which is nothing but I times z cube plus c. Some constant, I mean, right? And this is clearly an analytic function, right? Right, so many times if u is given and you can find v, the harmonic conjugate, right, such that the corresponding function is analytic anyway, right? These are two simple exercise. So actually when we are looking at analyticity of a function, we can actually also look at this kind of behavior, right? Because if and only if condition, okay, as I shown to you that 2xy plus I times x square minus y square is not analytic because it was not harmonic conjugate. One of the one, I mean the Cauchy-Riemann equations were not satisfied. Anyway, then there are some exercises. As an example, I would like to give. F of z is equal to e raised to power minus y sin x minus I times e raised to power minus y cos x is an entire function. Show that this is the entire function, means analytic everywhere in the complex plane. Another example, f of z is I times z square, z is not equal to 0. This is also analytic because z is avoided here, na? Another example, suppose uxy is given to you, x cube minus 3xy square minus 5y is harmonic. Find harmonic conjugate. Okay, so these are some examples for you to work on. T time problem के लिए छोटे छोटे हैं, right? So you can try to do these things. I think harmonic function का chapter खत्म. अभी तक हमने तुमको बहुत सारे functions के examples नहीं दिए, right? So the next thing is that I want to show you elementary functions. Like you have, what are the elementary functions that you know from your single variable calculus? Log function, right? Sine function, cosine function, exponential function, right? Hyperbolic functions and so on and so forth, right? अभी हम इन functions को complex के domain में define करेंगे, and then you will see, I mean we will define in such a manner कि अगर हम इन functions में where z is equal to x plus I y, if we put y is equal to 0, we will get the real variable case. Okay, for example, e raised to power z. E raised to power z is e raised to power x plus I y. If you put y is equal to 0, we will get e raised to power x. A single variable case, right? This is how we are going to generalize. But when we do this generalization, bizarre things will happen. What is the value of log 1? 0. पढ़ते आए हैं, right? Here log 1 is non-zero. Okay. And what is the value of log of e raised to power z? Normally it is z. Here it is not the case. So you see the, okay, beautiful things, right? So you observe a lot of beautiful things here. Elementary functions, okay? So now we are going to define functions in the complex plane. We are worrying about complex plane C, which is x plus iy, all numbers like this. So first of all, I am going to define exponential function. अगर आपको exponential function define करना है, what would you expect? सीधे लिख देते हैं e raised to power z. If z is a complex number, exponential function is e raised to power z is equal to e raised to power x times e raised to power iy is equal to e raised to power x cos y plus I times sin y. Agree? Exponential function. z is equal to x plus iy. Now you can see that the definition, the generalization is really valid, because if you put y is equal to 0, we get the real exponential function, right? So it makes sense. So whenever we are doing generalization, we should always do in a sense that if we take the special case, we should get the actual value, right, which is there in the real. Now, first of all, there are some properties or observations. E raised to power z is never 0. Do you agree? Because absolute value of e raised to power z is positive, right? So it is never 0. Second property, e raised to power z is periodic function. Periodic function. So because e raised to power z plus 2 pi I is what? E raised to power z. So period is what? 2 pi I. Right? It's a periodic function, right? I mean, you can just check. I mean, if you put 2 pi, because there is not, I mean, it's not going to change, it will give you the same function, right? So it's a periodic. यहाँ तक तो सब भी ठीक है, right? It's not much problematic. Now you see, can you say that the e raised to power x, if x is real, can it be a negative number? E raised to power x, if x is real, it cannot be negative, right? But here there exists a complex number z such that e raised to power z is negative number. So this is the first beauty, right? You see, e raised to power x is never negative, but there exists a complex number z such that e raised to power z is equal to -1, say, for example. Can you tell me what is that z? See why this is happening, because e raised to power x तो है, but साथ में वो cosine sin का expression भी है, right? So उसकी property will impact the whole definition, right? So let us see. So we know that, so we want to solve that e raised to power z is equal to -1. I want to actually say -1 कब आता है, for what complex number? So what I can do, I can write it down as e raised to power x into e raised to power iy is equal to 1 into e raised to power I pi, or pi I, that value is -1, right, always, right? So this implies that we will get e raised to power x is equal to 1, and y is what? Pi plus, not only pi, you can also take any 2n multiple, right, I mean of pi, right? Because that is going to give you same, because of cos and sin function involved, right? You will get the same value. So y is nothing but this actually, when we are comparing this and this in this, right? So e raised to power x is 1, this is possible when x is 0, right? And y value is always this, so this implies that your complex number is 2n plus 1 times pi I. Okay? For this value, e raised to power z is equal to -1. Right? Got it? कोई question? है ना beauty? You can see the beauty, right? Real exponential is not negative, but here e raised to power z could be negative. There are complex number for which I have taken just one equation, right? So when e raised to power z is equal to say -1, and so the z I can find out, right? by solving the equation. Another thing that you can note, if I can write down e raised power z as polar form. So r into e raised power I theta normally हम लिखते हैं, right? Here I am saying rho in and phi. R और theta की जगह rho और phi notation use कर रहे हैं. So where rho is e raised power x and phi is y, right? So here we get mod of e raised power z is equal to e raised power x, and argument of this y plus 2 and pi, right? Because that is not going to make any change. Argument is this value, right? Okay. So exponential के बारे में बहुत ही आसान था. We started with the exponential function, the most easiest thing, right? And we observed certain properties. अब एक्सपोनेंशियल आ गया तो इसकी मदद से हम लॉग डिफाइन कर सकते हैं, राइट? बिकॉज लॉग एंड एक्सपोनेंशियल आर इनवर्स ऑफ ईच अदर नॉर्मली इन द रियल केस, राइट? सो लेट अस सी व्हाट हैपेंस हियर इन दैट केस. अरे यार, logarithmic function. So what we want, find a complex number w and of course it is given that z is basically non-zero complex number. I am avoiding 0 here, such that e raised to power w is equal to z. E function जो अभी हमने define किया, exponential z function, right? So because we know that w acts as a log, if e raised to power log should be the actual value, right? Z. If w is some function of z, I want to find the definition of log. So w is some function of z, right? I don't know what it is, right? So but I know that it should satisfy this equation, that exponential of that function should give you z by nature of the log, log and exponent function connection, right? Right? Because e raised to power x, log of e raised to power x is what? X. Keeping say that idea in mind, I am trying to find a complex number w such that e raised to power w is equal to z. But what is e raised to power w? Just now we defined exponential function. Now let us see what is w. Beautiful function, you will see the beauty of this function, really very beautiful. शायद थोड़ा सा तुमको absorb करने में शुरुआत में दिक्कत आएगी, but it's really beautiful. I'll show you the picture also. Okay. So if z is equal to r times e raised to power I, z is equal to r times e raised to power I theta, कैपिटल थीटा यूज कर रहा हूं मैं, पोलर फॉर्म. सपोज पोलर फॉर्म में सब करना आसान है एक्चुअली, वेयर थीटा इज लाइक दिस एंड सपोज w इज इक्वल टू u plus iv. So I don't know u, I don't know v, I want to find w, right? So we can substitute all these things. So that means what we are going to get, e raised to power u into e raised to power iv is equal to r times e raised to power I. Agree? This is the value of z in the polar form, and this is the, I just substitute the value of w, right? U plus iv. So our job is to find the value of u and v in terms of r and theta, right? Then only we will be able to find the function, right? So from here e raised to power u is equal to r in the real case, right? So essentially u is nothing but log of r, real wala log, which is okay. You need to worry about this. And again you see that because e raised to power 2n pi I is 1, right, for any n, वो हम हमेशा यहाँ पे ऐड कर सकते हैं, right? So that means because if we don't add that, we are getting only one value, right? So that's not a general way. I mean, when we are solving the equation, which is solved in the totality, right? So I am saying that this implies that e raised to power u is equal to r and v is equal to theta plus 2n pi. Agree? Because e raised to power 2n pi I is 1, right? So I can always add this portion. Huh? So v is this and u is that. So clearly u is log of r. Okay? And v is this, right? This is our v. So combining these things, we are going to get, so this implies that e raised to power w is equal to z if and only if w is equal to log r plus I times theta plus 2n pi. अगर ये गड़बड़ हो रहा है बार बार, मैं दोबारा लिख देता हूँ बिकॉज ये इंपॉर्टेंट डेफिनेशन है. दे शुड नॉट, अरे यार क्या प्रॉब्लम है इसको. ओके, n is a integer. So e raised to power w is equal to z if and only if w is this. So this implies that we can define log function z is equal to log of r plus I times theta plus 2n pi. This is the definition of log function. Bit weird, right? Where z is r times e raised to power I theta, then expression for log z is like this, right? Any question? ये सबको समझ में आ रहा है log function? सिंपल है, कुछ है नहीं उसमें, खाली 2n पाई का खेल है वो है बस, बाकी तो सब स्ट्रेट फॉरवर्ड कैलकुलेशन है, हाई स्कूल का बच्चा भी कर लेगा, राइट? बट यहां से ब्यूटी शुरू होती है. नाउ यू सी व्हाट इज द वैल्यू ऑफ log 1. दिस पोर्शन विल बी 0 बट ये रह जाएगा. सो log 1 इज नॉन जीरो, राइट? है ना ब्यूटीफुल? So let us see some of the beauty. But this function is such that e raised to power log z is equal to z, right? So this definition of log z is like this. हमने exponential function define किया, उसकी मदद से logarithmic function define कर लिया, right? And so log z is if z is a complex number r times e raised to power I theta, log z is log of r plus I times theta plus 2n pi. N is an integer, right? Now, so actually I can write down also in terms of, so this implies that log of z, z is a complex number, can be written as log of mod of z plus I times argument of z. This is another shorthand form, right? Mod z is r and argument of z is theta plus 2n pi, right? Fine. Now note, observe that, So what is the value of log of e raised to power z? अभी हमने ये डेफिनेशन कैसे बनाई है? e raised to power log of z is equal to z, right? Exponential of log z is z. वहां से हमने बनाई है. Now I want to find out what is this value, log of e raised to power z. Any idea? It should be z, right? But it is not. So you see, this is not is equal to z. Why? Because, you know, if log of z is equal to log of mod of z plus I times argument of z, so I can just substitute here. Now when we are looking at e raised to power z, mod of e raised to power z is e raised to power x, and argument of e raised to power z is y plus 2n pi. We just saw this, right? N is an integer, right? So log of e raised to power z is equal to log of mod of e raised to power z plus I times argument of e raised to power z. This is log of e raised to power x plus I times y plus 2n pi. So log of e raised to power x will become x, so this is nothing but x plus iy plus 2n pi I. So log of e raised to power z is equal to this, which is z plus 2n pi I. So log of e raised to power z is z plus this quantity. अब क्या करें? ये तो पूरी कहानी बदल गई. हम तो स्टार्ट किए थे एक तरफ से, राइट? एक्सपोनेंशियल फंक्शन डिफाइन किया, एंड वी थॉट दैट सिमिलरली वी कैन टेक द log, right? E raised to power w is equal to z. I mean, that should be the definition we started with. We found the definition of z, but log. But then we try to check the other formula. It is not working. So actually, by now you must have observed that log is nothing but a multiple valued function, right? हर एक इस n की वैल्यू के लिए अलग अलग वैल्यूज आ रही हैं, राइट? राइट. सो हम क्या करेंगे? एक वैल्यू को फिक्स कर देते हैं, और सपोज n इज इक्वल टू 0, सबसे आसान केस. इन दैट केस व्हाट विल हैपन? ये भी फॉर्मूला सेटिस्फाई हो जाएगा, राइट? सो एक्चुअली log function is a multiple valued function, okay, and for each n we have different branches. For each n will give you one branch of the function, another n will give you another branch of the function, right? N is equal to 0 case, we call it as a principal branch of the function, right? So principal value of the log. So that log we call principal log. Okay, this log that we got, we defined is a general log, right? But हमारा काम आसान तब होगा जब हम प्रिंसिपल लॉग के साथ काम करें, राइट? देन एवरीथिंग रिमेन्स वैलिड. ओके, सो लेट मी शो यू दैट. So if we put n is equal to 0, we get principal log in that definition itself, right? Okay, दिख नहीं रहा है. Anyway, n is equal to 0, we will get principal log, and we denote it by log of z. कैपिटल L कर देते हैं यहाँ पे, ठीक है? is log of r plus I, log of r plus I theta. Okay, this is the principal log when n is equal to 0. उसी फॉर्मूले में हमने स्मॉल n is equal to 0 रख दिया, right? We get the one value. So log z, so that means log of z is defined, is well defined, okay? and single value when z is equal to not equal to 0. So when z is equal to r, I mean when z is a real thing, you get the real well definition, so no issue at all. Now you just check what is log of 1. General log definition that we gave is log of 1 plus I times 0 plus 2n pi. This is 2n pi I. So log of 1 is not equal to 0, right? But capital log of 1 is 0. Okay, capital log of minus 1 is pi I. So all these variations you can do, right? So everything works fine when we look at the principal log. So there are principal log is single valued when n is equal to 0. We are on one branch, well defined function. Otherwise log z जो हमने बनाया है, it is multiple valued function, right? So there is another interesting concept here. So basically, in order to define it nicely, what we can do here, if z is equal to r times e raised for I theta, non-zero in C, so theta is equal to capital theta plus 2n pi, n is integer and capital theta is argument of the, remember argument were also two kind, principal argument and right. So in that case log of z is equal to log of r plus I times theta plus 2n pi. I am just summarizing everything. So if we restrict, actually if suppose alpha is a real number, I can actually restrict everything. And theta lies between alpha and alpha plus 2 pi, a cycle of 2 pi actually. Then log of z is log of r plus I theta, where r is, so this is the actual definition where theta lies between alpha less than theta less than alpha plus 2 pi. Any cycle. So this is a definition of log, right? So actually I will show you. So all these branches, I think I have a picture here also, I can show you somewhere. I hope it will come. Yes. Here is a picture of log z function. You see there are different branches, right? For each n we have one branch. You can keep on moving. ये दिखाने का तरीका ऐसा है, right? I mean, but you can imagine, right? ठीक है? एक beautiful चीज़ है इसमें. In all branches, one point is there which is common to all branches. Which point is there in log z के केस में? Which point is common to all branches? Anyone in the class? हाँ, ये इसको आत्मसात करना बहुत इंपॉर्टेंट है एक्चुअली. मल्टीपल वैल्यूड फंक्शंस का जो हम प्लॉट कर रहे हैं, वी हैव डिफरेंट ब्रांचेस. वन पॉइंट इज कॉमन टू ऑल ब्रांचेस. व्हाट इज दैट पॉइंट? ज़ीरो. ज़ीरो सब में कॉमन है, राइट? सो ज़ीरो को एक स्पेशल नाम दे दिया है ब्रांच पॉइंट. ओके, व्हाट इज ब्रांच पॉइंट? ज़ीरो इज़ अ ब्रांच पॉइंट. और क्या है कि चूँकि एक सेपरेशन रहे इन ब्रांचेस में, तो हम एक कट बना देते हैं एक्चुअली. ओके, नॉर्मली वी कट इट. आई विल शो यू इन द अदर वन नाइसली. सो एक ब्रांच से दूसरी ब्रांच को सेपरेट करने के लिए जो कट होता है, तो नॉर्मली एक्स एक्सिस लेते हैं, इज नोन एज ब्रांच कट. ओके, बिकॉज इट्स अ मल्टीपल वैल्यूड फंक्शन, You cut it at one point, okay, so that everything remains well defined. So if you are in one branch, normally we take principal branch, everything is okay. And this kind of diagram is known as Riemann surface. Riemann surface of log z function. Why we are able to do this? Because log z is a multiple valued function, okay. So we want to fix one branch, okay. And so whenever we are fixing on one branch, of course we need to do a cut, branch cut, which will separate the branches, right. And one point which is common to all branches is, actually it's a singularity. I'll show you why it is singularity, that z is equal to 0 is a singularity. So I think I will take, when we take the exponential function, like I will take square root of z, then you can also feel the beauty of square root of z. That is also a multiple valued function, okay. So how do we define that and so on, right? That we will do in the next class. Thank you.